Hello, my name is Junhyun Kim, and I am currently a PhD student in the Department of Computer Science and Engineering. Today, I will talk about my paper, All You Need is Attention, Lightweight Attention-based Data Augmentation for Text Classification, which was published at EMNLP 2024 Findings. First, let me introduce the lab I am affiliated with. I am a member of the Software Security Lab led by Professor Sung-jae Hwang. We are interested in hacking, security, program analysis and testing, and empirical studies. You can find our lab's URL and contact information here. If you are interested in our lab, feel free to contact us using the provide details. Machine learning is incredibly popular field these days, and one of the most critical factors in this domain is the quality of training data. In cases where obtaining sufficient training data is challenging, such as in medical applications or privacy-sensitive domains, data augmentation is widely used. Data augmentation is a technique to increase the amount of training data, but unlike oversampling, which simply duplicates existing data and leads to repetitive learning, data augmentation generates new data that differs from the original. This helps machine learning models learn from more diverse perspectives, improving generalization and mitigating overfitting by providing meaningful and varied training samples. Originally, data augmentation was widely used in computer vision at the image level, but it has also been studied for text data level. In this study, we categorized text data augmentation approaches into 3 categories. The first one is the noising method. This noising method involves adding simple noise to a sentence, such as EDA, the easy data augmentation, and AEDA, an easier data augmentation, being representative examples. EDA consists of 4 operations: synonym replacement and random insertion, a random swap, and random deletion. It randomly selects words in a sentence and applies one of these operations. Synonym replacement and random insertion utilize an external dataset called WordNet to find and insert synonyms. AEDA, an easier data augmentation, is a simpler approach than EDA. Instead of modifying words, it randomly inserts one of 6 punctuation marks at different positions in the sentence. The second category is model-based methods, which operate based on language models. Representative approaches include contextual augmentation and conditional BERT, CBERT. These methods perform synonym replacement on randomly selected words in a sentence. However, unlike EDA's synonym replacement operation, they consider the sentence's label as conditions to ensure that the context remains intact. Contextual augmentation considers the probability distribution of word embeddings when replacing words. And CBERT improves upon contextual augmentation by adding the sentences label as a condition, ensuring that the substituted word aligns with the label. This helps generate label-consistent augmented data. Additionally, in CBERT, a masked language model, MLM, is conducted with these conditions, allowing for more contextually appropriate word choices and improving model performance. The third category is interpolation methods, which combine two input words or sentences similar to mix-up in image data augmentation. Word mix-up performs mix-up at the word level by interpolating between the embeddings of two words. It randomly selects and mixes characters within each word based on a value of lambda. And send mix-up extends this approach to the sentence level, interpolating between the embeddings of two sentences and mixing words according to the lambda. Since these methods mix tokens at the same positions, they may not always produce contextually coherent sentences. To address this problem, a pre-trained model is used at the final step of this process to predict the label of the generated sentence, ensuring the augmented data remains meaningful and remains its context. Unlike the previous methods, our study proposes a new approach of text data augmentation. The LADAM stands for a lightweight attention-based data augmentation method that leverages attention scores for data augmentation. Our method randomly selects a word from the target sentence T and replaces it with the word from an additional sentence A that has the highest attention score from cross-attention between two selected words. The figure 1 provides a simplified process of our approach. First, we randomly select a target sentence T from the dataset for the data augmentation, and then next we choose an additional sentence A that shares the same label L as the target sentence. Using cross-attention, we identify the words in A that have the highest attention scores with words in T, then swap them accordingly. Before proceeding further, let me briefly explain the attention mechanism used in this process. The attention mechanism is a method that learns the relationships between words in an input sentence to generate more accurate outputs in the decoder. For example, let's consider translating the sentence, "I am a student." The encoder converts each word into an embedding vectors and learns the relationships between words. And then the decoder generates a new word at each time step by performing cross-attention with the encoder's output to determine which words to focus on according to the relation. For instance, when translating student, the word student, the decoder learns that student in the input sentence is the most relevant word and generates the appropriate translation accordingly. Thus, the attention mechanism dynamically adjusts the weight of input words, enabling contextually accurate translation. And in our method, the LADAM, we learned the relationships between the target sentence T to be augmented and the additional supporting sentence A. This enables us to identify and exchange words with the highest contextual relevance for replacement. We will use the BERT-VIS tool that visualizes the cross-attention mechanism to provide more illustrative examples. This tool visualizes the cross-attention, as I said, which we utilize in LADAM by connecting words in the target sentence T and additional sentence A based on their highest attention scores. For example, here, consider the two sentences as target sentence, the cat sat on the mat, and additional sentence, the cat lay on the rug. In this case, the word the in target sentence is most strongly related to the in the additional sentence A, as both words serve the same role in their respective contexts. And the same applies to the second word cat. For the third word set, the highest attention score in this case is assigned to the special separator token SAP. But since the SAP token is not a word that we can replace, the LADAM selects the next highest attention scored word, which is lay here, and performs the substitution accordingly. We can observe that cat also has a relatively high attention score, as cat is the noun performing this verb. However, in this case, lay has an even higher score since it serves the same functional role as sat in the additional sentence. Thus, in LADAM, we aim to exchange words with semantically and functionally related counterparts, ensuring that the substituted word plays a similar role within the sentence structure. So, the figure 1 is an example of how cross-attention is used to replace a word in our approach LADAM. Here, we use the sentences a cat sat on the mat as target sentence and a dog lay on the rug as additional sentence A. From the target sentence, if A is chosen to be replaced, then it is replaced with on, as they have the highest attention score. If cat is chosen, it is replaced with the word dog. If mat is chosen, it is also replaced with dog, as the attention mechanism identifies it as the most related word. Through this process, augmented sentences are generated, creating synthetic text examples that maintain meaningful relationships within the sentence structure and maintain its context. Our experiment evaluates the impact of the data augmentation approaches by following these steps. First, we apply different data augmentation techniques to each of the data sets. And then we fine-tune pre-trained models, BERT model for example, on the augmented data set. And then we compare the evaluation performance across different augmentation approaches. This approach allows us to assess the effectiveness of each augmentation techniques and analyze its influence on model performance. The datasets used in our experiments are primarily designed for sentiment analysis. These datasets include the CR, the customer review, a dataset of electronics product reviews, and SSC2 and SubJ are both movie review datasets from IMDb, where SST2 focuses on binary sentiment classification and SubJ on subjective or objective classification. MPQA is collected from news articles commonly used for opinion polarity classification. And TREC is a dataset consisting of questions typically used for question classifications with 6 classes. This table 1 provides an overview of the statistics of these datasets. Next, we introduce the baselines and models used in our experiments. For baselines, we selected the most popular data augmentation approaches based on citation counts and GitHub stars. From the previously discussed methods, as I aforementioned methods, EDA and AEDA, CBERT, SEM mix-up with our method LADAM are selected for our baseline approaches. These methods serve as strong baseline comparisons for evaluating the effectiveness of our proposed approach. For fine-tuning, we primarily used BERT-based model as our basic experiment, the base models. Additionally, to examine how results change when using different classifier, the different model architecture, we also experimented with Roberta, DiBerta, and distilled BERT models. These models were selected because they achieve a state-of-the-art performance in text classification and sentiment analysis tasks. By testing across these models, we can observe how our augmentation method impacts various model architectures. The table 2 presents the F1 scores obtained after applying each data augmentation techniques to the full data set, fine-tuning BERT, and evaluating on the test set, each test sets. Our proposed method, the LADAM, achieves the best performance in all cases except for TREC. For example, the LADAM achieves 95.70 on CR dataset and 98.12 on SST2 dataset. Also, it achieved 98.74 on sub-J datasets. On average, LUDM achieves an F1 score of 96.01, making it the highest performing augmentation method across the datasets. The Table 3 also presents the results of applying each data augmentation method after reducing the dataset size intentionally. For each dataset, we reduced the data for all but one label to 1/10 of its original size, the 10% of the size. Then applied data augmentation and fine-tuned on BERT on the augmented dataset. In this biased dataset setting, our method LUDM achieved the best performance on CR, SST2, and sub-J datasets. But for MPQA and TRC, our LUDM did not achieve the highest performance, but also other methods did not show the significant improvements too. Overall, LUDM achieves an average F1 score of 87.21, demonstrating that it maintains the best performance even in biased datasets settings. And these results show the fine-tuning performance across various model architectures. To facilitate comparison, this figure 2 presents the average performance across all datasets, all full datasets for each model. Our proposed method, the LUDM, consistently achieves high performance not only with BERT, but also across different model architectures. This demonstrates the robustness and effectiveness of our approach across various pre-trained models. And figure 3, in this part, the figure 3 visualizes the impact of LUDM on sentence context preservation by comparing the original dataset with the augmented sentences generated by LUDM using locally linear embeddings, the visualization. In this visualization, LLE, data points of the same label are represented with the same color, and the larger markers indicate the original data, while the smaller markers represent data generated by LUDM. With this figure, we can observe that sentences generated by LUDM maintain a data distribution similar to the original dataset. And it demonstrates that our augmentation method LUDM preserves sentence context while generating diverse samplers. In addition to the previous experiments, we conducted an evaluation study by modifying specific components of LUDM to assess their impact on performance. This experiment examines the impact of number of augmentation, which controls how many new sentences are generated per original sentence using LUDM. By varying these parameters, we analyze how the amount of augmented data affects performance. Note that in all other experiments, the number of augmentation (NAUG) was set to 2 for all other data augmentation methods, the experiments. The results show that when generating 8 or more augmented sentences per original sentence, the model achieves performance close to the optimal level. This suggests that LADAM does not require excessive augmentation for effective performance, for the optimal performance. And this ablation study examines the impact of skipping certain processes in LADAM during augmentation process. We conducted two variations, LADAM version A and LADAM version B. LADAM version A replaces words instead of swapping words based on attention scores. It means randomly swap words between two input sentences. And LADAM version B replaces all words from target sentence T instead of swapping a single word from a target sentence T. From the result of LADAM version A, the performance was slightly lower than the original version of LADAM, indicating that using attention scores for replacing words, the swapping words, is quite beneficial. However, interestingly, even performing random word replacement, random word swap across two sentences showed better results than some existing augmentation methods, suggesting that this sentence level swap, the framework itself, is quite a useful strategy. And also, for LADAM version B, the performance dropped below even the baseline model trained on the original data set without any data augmentation. This suggests that applying too many replacements across all words, it negatively impacts sentence coherence, sentence context, making the augmentation less effective. It harms the context of the original sentences. The results indicate that limiting replacement to a single word per sentence is a more effective strategy for generating high-quality augmented data in our LADAM method. For the conclusion, this paper proposes a lightweight attention-based data augmentation method, LADAM, that leverages attention scores while the data augmentation process. Our experiments demonstrate that our LADAM outperforms other existing text data augmentation methods in classification tasks. This study also provides evidence that attention scores can be effectively utilized in the field of data augmentation on text, highlighting their potential for improving NLP model performance. Thank you for listening my presentations.